Welcome back to SEEK Bytes, a podcast for software engineers by software engineers. On this episode, we're joined by a guest coming to you from Sydney over Zoom. His name is Ren. He's one of our staff engineers in the Artificial Intelligence Platform Services team. We'll talk a little bit about how to get into systems engineering, what is a systems engineer versus a big data engineer, and also latency numbers every programmer should know. Welcome back. We're here with the terrific trio. I'm your host, Seamus. We've also got Elliott.
Hey.
And Will.
Hello.
And our special guest, Ren. Thanks for joining us. Do you want to talk a little bit about what you do at SEEK? Let people know.
Yeah, sure. My name is Ren, and I'm staff engineer in the search team inside AIPS. Day to day, I kind of work in my team to help build the search engine for SEEK. And that's a big topic.
Does AIPS have a meaning to that?
Yeah,
acronym?
what is AIPS?
Yes, that's a good question. Artificial Intelligence Platform Services. It's a quite big department. So what we do is we build some of the core services for the SEEK marketplaces. So some example would be like job search engine. So we build the kind of search API to support the marketplace. And there will be another team to build a recommendation engine and another team to build like the candidate badge. So there's a couple of those kind of services that's to support the marketplace.
Basically anything at SEEK that could be driven by some kind of model, some kind of, data-driven decision-making things is what AIPS covers, right? Cool.
We usually call them AIPS as well, right?
AIPS, yep.
I'm just stuck on the term engine. My head just immediately went to kind of like car manufacturing, and I'm like, how can I like phrase this for my partner to be like, this is what it's like? I was like, is AIPS like the manufacturers and they like build all these different engines, or it was like the engines are the things that build things? It's a factory. I'm like, oh, how can I phrase this?
Yeah, how would you describe your role, your team to someone who isn't so focused in engineering? I know it's an engineering podcast, but different skill levels.
The team I'm working is very interesting. We are basically, when I said build job search engine, if you imagine when people come into the SEEK website, there's basically two text boxes in there. One box would be for you to type in a query. So for example, like accountant or 17-year-old or something like that. So you're basically typing some keywords in, and the intention is like the candidate wants to find some jobs related to that. And what the search team does is we are eventually receiving that query, and we need to go through those jobs and in SEEK Australia to go and find the most relevant jobs for that query, and then sort of rank them and then basically return it back to the user. So if you kind of think about from engineering point of view, we provide an API endpoint where we receive the query and we'll return those jobs.
So when you say you kind of receive that query, is that like a real-time thing? It's not like pre-aggregated results. It's like, no, you get the query and then you have to like really, really, really fast filter that down to give accurate results back?
Yeah, exactly. That's right. So kind of this is one of the kind of main challenging that we're facing, or we're trying to solve, is that how do we make the job search really, really fast? On average, we receive a couple of hundred queries per second. So this is in aggregate of sort of SEEK Australia, and we've got our Asia brands like JobStreet and JobsDB in Asia. So all those brands and those marketplaces, all the queries come to us. So in the peak, we receive a couple of thousand requests per second, and we want to be able to kind of process them and return them really, really quickly. When you type in something to search, you don't want to wait for a couple of seconds before that results come back. We've got this user kind of expectation where they really want things really fast, and it's really important. But even if you look at how this whole thing's built, there's many layers of infrastructure in there. So the front end needs to build the HTML page and to render that. And then some middle layer service will call us and return the results. So all this add up. So we can't introduce too much latency in our layer. So the whole experience is still snappy and really fast.
So I guess from when people think about AI, or I guess AI engineers, a lot of the time people just assume that you're the ML, like you're writing the machine learning algorithm, you're creating the weights, or you're doing the training, that kind of stuff. But that's usually the data scientist, right? So from an engineering perspective, what you're responsible for is connecting the experience to the model, all of the plumbing and infrastructure around that. But it sounds like primarily doing that in a very efficient, very fast manner.
Yeah, we can touch a little bit about sort of working with data science area a bit later, but maybe just a quick kind of a few bullet points around that. If we talk about, let's say, say 20 years ago, or 10, 20 years ago, the search is mostly just like text match. So you type in kind of text to say accountant or whatever, or a job title, say, receptionist or kind of pizza delivery driver. So we're trying to really match the text in the job title and content, and we return that. And that is a very naive and basic way to do it. But these days, we use a lot of machine learning models to try to understand the intent of the query, and then to try to match it with the job content. So sometimes your keyword might not appear in the job content. So that involves sort of a lot of data scientists building machine learning models. And what the engineers do is to look at those machine learning models and how to run them in a production environment, and to still make sure it runs really fast. That's sort of one thing we do. And the other thing we do is kind of really helping the data scientists to build tools. So one example would be, so data scientists might need to grab a lot of historical data. So like, what are the jobs the user have searched in the past, and what are the jobs they actually clicked on, and things like that. So they use that to build models. But in order to do that, they might need to replay those logs and to run those things. And we built some of the tools to let them kind of operate those big data efficiently, so they can kind of grab the data, do some massage, and put into their model or transformer model, whatever, to produce some model that can be used in production.
So that's really good insight. Thank you. So it's not just the infrastructure for connecting, the experience to the models itself. It sounds like it's basically any kind of tooling that the data scientists might need as well to help better facilitate the role that they play in this, right? Like you were saying, it's the extracting of the data, giving them the tools and capability to easily be able to interrogate the data that we have, and to be able to add that to the model and feed that into the model, basically, right?
I just want to go back for a sec. So we're throwing the term model around a lot, and what does that actually mean in this particular context? So when we think about model, it's usually something kind of data-ish related, right? So when you're interacting with these sorts of models, Ren, what does that actually look like? What is a model in this context?
So I'm personally not a machine learning expert, but I'm trying to use maybe a metaphor, try to explain it in my way. So see if it makes sense to you. If you think about, let's say in the past, we've got lots of queries like, the example I mentioned, 17-year-old jobs, okay? The machine doesn't really understand what that means, but if you, as a human being, we can think about it as in, it's probably some jobs suitable for kind of teenager people to do part-time kind of jobs. So how do we make the machine understand that? One way we do that is to look at the historically, like people might type in that word in the past, and we look at what are the jobs they actually interact with. So we use that knowledge to infer those are the jobs that might be probably related to that kind of particular query. So we basically built some of the connections using the historical kind of user behavior. So that model will basically kind of draw those connections, and then you can use that in the production environment to make the job search more relevant. So in future, we can understand those kind of intent.
So we might kind of describe it then as kind of a decision tree that we've built up, right? To you could enter in many places in the decision tree based on what your original kind of query is, and that kind of tries to determine which of those decisions would be the highest probability of being correct.
Yes. So sort of decision tree or maybe like a regression tree, that's one of the classic kind of method or technique the data scientist uses to build models. That's one of the models that we have. Yeah.
Very cool. So there's more.
Yeah, it's funny because like I studied AI at uni, rudimentary AI, like AI 101, like what's a heuristic, that kind of stuff. So not like, not really looking at neural networks or machine learning, well, very, very, very rudimentary machine learning, that kind of stuff. And I still am, I struggle to get my head around what this looks like. I mean, as an engineer, I feel like we naturally try to create a very concrete model of a thing. And that was something that I found, I think a lot of people struggle with at uni, especially when you're doing computer science, is these very theoretical concepts. Like on paper, on a whiteboard, you can draw these boxes and give them names and be like, this is the model. But it's very hard to draw a concrete understanding or concrete representation of what that model actually is. So you talk about like a regression tree, and we understand, I mean, for anyone who doesn't know much about AI or hasn't heard these terms before, there's things about like weighted nodes on a graph. So the idea is that you're moving through a graph until you find the most heavily weighted result, and that's the result that propagates back up to the query as the response. But again, that's very theoretical. What does it actually look like in terms of code? And I guess that's the model, right? Like this is the part where the data scientists are the ones who have a very concrete understanding of that, and where our understanding sort of remains in the theoretical, right?
Yeah. I think this is the part that I feel like really passionate about. And I think it's one thing I really loved about kind of joining and being working the team is that is how do we make the data, how do we make the system run really like efficient and fast? So maybe I'll touch a little bit based on kind of this concept of product engineering versus system engineering. So kind of maybe a little bit about my background. So before I joined this team, like 3 years ago, my entire career was kind of based on working on web apps. So like a full stack web app engineer. So imagine, building some HTML and writing some sort of web routing layer, this action, go to that, and probably using some database to save data. So that's a typical kind of stack. And what I found when I joined this team is that day to day, I spent a lot of time thinking about what data structure do I use to solve that particular problem. And so often there's not existing libraries that just does that. So I think a contrast between like now and before was like before. So what I would call myself as a product engineer. So my focus is to kind of ship the product features, like some user-facing features or some APIs where the app will consume. And you're thinking about what data do we need and how do we fetch it from database and give it to the API, for example. And the way how I do it was that mostly just thinking about, is there any library I can use? Is there any existing database I can use? Things like that. But these days, working in the search team, I would call this as a system engineering, where you can't just go and use a database to do that because it just doesn't fit. So we have to often build a database or build a particular data structure to solve that problem. And I find that very fascinating. So maybe I'm trying to think about an example, maybe one example I can give. We want to be able to build a radius search functionality. So basically, imagine we have a search engine index lots of jobs, and we want to build a filter where you specify a radius, say, from Sydney's CBD, we want to draw a 10-kilometer radius, and we want to find all the jobs in that kind of radius, right? That's actually not easy. So you can't literally iterate every job and just compute the distance. That would be too slow. And one of our engineers, he found a very smart way to do that. It's a technique called GeoHash. So essentially, you can compute all the location of the job down to an integer, not an integer, just a number. And then you can basically do kind of a binary search, a way to just narrow down that jobs in that kind of radius. That's like one example of some of the problems we're solving. Yeah.
So in that scenario, would you run a job that would basically iterate over all of the... So you're talking about creating the data structure to best suit the kind of query. So I'm trying to connect what you're saying before to what you're saying now. Would you run a job that basically iterates over all of the job postings in the country and then creates or like inserts basically maps them from, whatever the location ID or whatever geohash or whatever into a new data structure that is these single integers or these single numbers. And then I guess maybe you have a map you can just interrogate between these values, get all of the values between, index A and index B, and those are all the ones within that geohash, within that radius, within Sydney?
Yeah, I think that's kind of roughly the idea. So imagine all the job we index, they have a geohash, which is essentially just a number. And all you need to do to run this radius search is imagine you have a number, between 0 and 1,000. All you need to do is say, Sydney is somewhere between 500. So you would say, let's say Sydney is at the number 500. That's Sydney's like geolocation there. And you would say 10 kilometers around Sydney would be between 480 and 520. And so you can basically go and do this binary search and find all the jobs between 480 and 520. And that's a very, fast.
Yeah.
That's really fascinating.
Yeah.
Is this related to that doesn't sound to me like an AI thing though. Is it?
So you're right. This is not a AI thing. So like what I said, a lot of problem we're solving is more related to computer science, as in just more like classic computer science, but applying a modern hardware architecture. Like how do we use those algorithms or data structure to make it easier for us to like operate AI?
Yep. So
really
this is just
interesting.
one component that falls into the network. So you might have multiple different facets or multiple different algorithms or whatever that the query is passing through, and this is just one of them. Where part of that query is within a 10-mile radius within Sydney. So you're hitting that part of the. I'm trying to
Signal, maybe it kind of like matches the signal. Well, I know Google.
Yeah, so this would be like more like a filter. So when some people, when doing a job search, they would like to specifically only looking for a particular area. So that's like one filter that we...
Yeah. And then the AI component might be like role title normalization, natural language processing, turning a human written query, 17-year-old jobs, into jobs for 17-year-olds. Like translating the 10 or 100 different ways that a person can ask the same question into one normalized query that you can pass into a model.
Yeah, so for that 17-year-old kind of example, I think how that problem is solved is more around you would use historical data to train the model, so they kind of understand that which job. So when we train the model, let's say we've got the model, and then when we ingest the new jobs, the model will look at the job and will say, is this job related to the 17-year-old job query? And it will give it a score. Let's say 0 being totally not related and 1 being it's totally related. So the model is able to kind of produce that kind of signals. And then we will then use that signal to determine if the job should be returned next time we see this query.
Based on like you were saying before, the activity of the user on the site. So someone who searched for 17-year-old jobs, what jobs did they click on? You get 1,000 or 1 million users with a similar query. Look at all the jobs that they've interacted with, and then you use that as a success value, and then you train the model against it to say jobs that fall into that same category, like jobs with the same titles, whatever, jobs with the same descriptions, whatever, like some attributes of those jobs is how you determine that they match.
Yeah, that's right. Yeah, so like for example, maybe some of the historical data we've got is like when people search for 17-year-old, they might click on maybe pizza delivery or maybe some, tutoring part-time job, that kind of things. So and then the model will learn that those are related to that concept later on when we can sort of use that model to serve the search request, so we can kind of draw those connections and bring those jobs up.
Each time a candidate comes in and searches for that same search again, are we continuing, like, is it a real-time thing where we're constantly updating the model? So let's say today I go in and say 17-year-old jobs, you propagate up 10 different jobs, and I only interact with one of them. Are we real-time doing this, or is it, once a month we're collecting a bunch of data and then evaluating it? Or is it every time a candidate comes in and interacts with the site, we're constantly updating those weights?
Yeah, so at the moment, we're doing that periodically, so it's not real time, but every now and then, we wanted to make sure our model is fresh. So things like, if there's a concept of COVID or work from home. So if we train that model before COVID happens, like when people search for COVID, the model doesn't really understand the concept. So after a while, we kind of need to retrain the model with those new concepts, and the model will understand it.
So what's the advantage of, or I'm not sure if you know or not, but answer to the best of your ability, what's the advantage of not doing it real time, of doing it like as a once a month, like refresh, where we refresh the models?
It's mostly just, there's a lot of kind of tuning and adjustment we need to do, so which makes it like not practical to do it real time. Right. So one example would be the responsible AI. So when we train the models, we want to be able to make sure it's like kind of not biased. If I kind of, like one example would be, recently we got some queries that were really long. Example would be like, my name is Emily and I want a job near beach, something like that. So we got this query, we need to respond with some jobs. But if someone coming and type a query, say, my name is Lachlan and I want a job near beach, if we return different results, that would be a bit of problematic because it feels like maybe we're heading for different job for female and males. So we want to be really careful about not creating bias in our models. So, which is why we introduce a couple of steps, checks when we prepare the model. So that's really important, which is why we don't want to do it real time, like automatically refreshing.
Right, because it gives the engineers the opportunity to do a bit of data sanitization to avoid things like bias in the model.
Yeah, exactly. So it's sort of engineer and data scientists kind of work together to make sure, this doesn't happen. And yeah.
So how do you, this is coming from my naivety in AI, but how do you catch stuff like that? Like, how do you catch it, like hallucinations or returning data that is obviously not correct?
We have a dedicated search quality team. So we have dedicated we spent time to look at and like manually evaluate the results. We sometimes even rely on some of the, say, ChatGPT to assess the results, and plus some human effort to do that and make sure it's, fine. Yeah. So it's not like magic. Just like imagine we just have someone, like even I built this model, I go do some search just to look at, does that make sense, or are we biasing on something? And yeah, so
I can't help but think back to one of the comments earlier about the, using a binary search. And I was like, I don't think in my professional career I've ever actually needed to implement any sort of proper search algorithm ever. Like binary search, A star, Dijkstra's, breadth first, depth first, et cetera, et cetera. So it sounds like clearly there is a need to do that. So like, the classic kind of thing, it's like, oh, is it quicker than bubble sort, or, whatever the memes were.
I mean, like, in casual engineering conversation, when you're working on web apps and stuff like that, you'll sometimes hear like, oh, I'm never going to need to know that. I'm never going to need to use that ever again. I spent so much time learning for those exams what the different sorting algorithms did, and we all joke about it. And then you talk to someone who's in AI engineering, like, no, that's my job. That's 90% of what I do is thinking about the efficiencies of algorithms.
It's actually very fascinating that I feel like I never had to touch any computer science stuff before I moved into this team. And since I moved into this team and I need to deal with this kind of, not on a daily basis, but maybe, monthly basis, I found it's really, really refreshing. And I think one thing I found that is even like there's a lot of things where it's like a solved problem. You think, okay, do a search, like do a sorting, like maybe doing a quick sort is like probably the fastest way to sort. But a lot of times on paper, you've got this big O notation. Okay, this got this n log n and complexity, but in reality, there's still there are a huge difference between like how you implement something. Maybe I'll give an example of how we actually make a one sorting kind of 10 times.
If I could jump in, could you explain for everyone listening what big O notation is?
Okay, so big O notation is more like a sort of classic computer science concept to describe the complexity of an algorithm. So basically, if we talk about iterate through an array, and then the complexity will be O(n), because basically you go through that sort of once.
Yeah. Or if you're going to iterate over it twice, then it's O(n) squared. And then, if you're going to, for every element, you're going to iterate over the array again, it's O(n) squared.
So let's say if you wanted to do like a matrix kind of, so if like O(n) squares, like if you want to, so something like that.
I just thought that's relevant because the fact that you mentioned Big O is kind of highlighting that you're definitely working in the realm of classic computer science problems, because you're thinking about complexity on like how do I represent complexity in a very short form way to explain to my colleagues like, oh, this is an O(n)(2) algorithm, or this is a log2 algorithm, or this is an O(n) algorithm. So like you can very quickly understand, the scale of complexity. If this has a million entries, O(n)(2) is going to be like much less efficient than O(n) or log. Yeah.
The only time I ever really think about that sort of stuff is when I'm like, it's in a dictionary. It's like, it's got an O of 1. It's like, here's your key, here's your value, done. It's like, do we have it in an array or a dictionary? It's like, well, if we have the key, use a dictionary. Bam, efficiency sorted. I've saved myself 0.00 milliseconds.
But then you think about it, is it really O(1)? Because it has to go through all the keys and find the key that matches. So how does it do that efficiently?
I mean,
that's where you get things like,
that's a great question.
Tree navigation and things like that, right? Like you can sort your keys into high value, low value. If it's a low value key, you can just jump half of the map and go straight into the low value of the keys, that kind of thing. See, we don't think about it on a day-to-day basis because other people have built, like Ren was saying, packages for us. People have built languages, like TypeScript has map. So we don't have to think about how to do an efficient way to navigate a tree of keys and values and find the key that matches. We just say map.key equals blah. But they have to think of how to do this because for them, the data structure itself is not, it's unique, right? You're creating your own data structure. So you have to think of how to traverse them.
When you're using a data structure, you're not, like, as I said before, it's not really created equal. So you really, if you really understand how that actually works on a modern sort of hardware, you actually gives a lot of inspirations to how to make it even run faster. So maybe the example I was going to quickly talk about is just a sorting one. So all the programming languages that you use mostly will provide like a sort kind of built-in library method, and it will just use like what's the most efficient kind of, from a computer science point of view, sorting kind of algorithm to do that. So it would be mostly a quick sort or a merge sort. So the complexity will be like n log n. So basically the idea is for the quick sort is you divide that list to half and then you pick one and say, all the elements smaller than this one go left and all the ones bigger than that one go right. And you continue doing that until you get the list sorted. That's a basic idea. So maybe the example I want to talk about is that we're basically relying on we use Java. We rely on Java's default sorting method to run that sort. And So during our profiling, so we look at the application, we notice that this sorting takes a long time. And it just doesn't make sense because it should be fast. It's got quick sort. So we dig into that and we look at like a flame graph. Basically, we look at how much time is like what is it actually doing during the sorting. We notice that 90% of time during that sort method, they're spending on comparing elements. So imagine you have a list of elements because they spend a lot of time comparing A and B, B and C, and like that. So that is very surprising to me. So we basically dig into like why this comparing is so slow, and we notice that. So, okay, maybe I'll give you a little bit background. So how it works is that what we wanted to sort is basically a list of jobs. And so each is basically a list of job IDs. Each job ID is an integer. And then each job ID has a relevance score, the relevance score being a number. And we want to sort them by descending. So the highest relevance score in the front, that's what we're going to do. But however, the data is basically stored in a hash map. So the key of the hash map is the job ID, and the value of the hash map is that job's score. So every time when we're doing the sorting, when you compare, you need to perform a lookup in the hash map. So you have to find the job ID to find its value. So you might think that, okay, hash map lookup, that's O1. That's a very, very fast operation. But in reality, it's not. You still need to perform like a memory lookup to find where it is and then going there and find it. And by doing this many, many, many times during the sorting, it's actually slow. A very simple optimization what we did is that instead of storing the job ID and the value in the hash map, we basically put the job ID and the score together, just like in one object. Every time when you do a compare, you find the job ID, you find that object. Because the score and the job ID is stored together, it's already loaded into CPU cache. It doesn't need to perform another memory lookup. So suddenly it becomes like 10 times faster. Maybe just on that, I want to pause here to mention there is a thing called latency numbers every programmer should know. I don't know if you've heard about that. There's a series of numbers, say, I'll think we can include that in the show notes. So I'll just read out a couple of kind of numbers in there. So L1 cache reference is 0.5 nanoseconds. So L1 cache reference, meaning if you loaded something into CPU cache, it's really, really fast to kind of, read it again. But main memory reference is 100 nanoseconds. This is like 200 times slower than, reading something from a CPU cache. So the idea, like the optimization that sort of was applied that, right, instead of every time you compare something, you have to go to the main memory to look up that, you just have that in the CPU cache already. So it's much faster.
That's really fascinating. I love this stuff because this is why I studied computer science. Like that's the kind of like crazy thing that we don't get to think about as web developers. Like we just don't have to think about the efficiencies of the memory on the chip and how it's the fastest possible memory you have access to. So if you can put something in there, that's like looking up something in L1 cache is going to be the fastest thing you can do. And then RAM, and then hard drive, and then different classifications of hard drive like solid state, M.2, spin disk, tape drives, whatever. These all have tape drives now. Like we're going back a ways, but you know what I mean.
What's the memory efficiency of a floppy disk?
Oh, I was just thinking that, and I was like, is it better than the zip disk? I want it, but you're totally right. And it's funny. Just as Ren was saying that, I was just like, L1 cache. I can't remember what that means anymore. Is that is that onboard memory? I was like, how much memory does an onboard CPU
on the
have?
chip?
I'm like,
yeah. Well, there's like L1, L2, and L3 cache, right? And they're different sizes. So they've got slightly different speeds, but it's not something we ever have to think about, really. But that's really fascinating. That the idea that you would combine both the value you care about and the key, so that when it reads it, so like the hash map itself, like generally speaking, when you're looking at a hash, the way that it works, and correct me if I'm wrong, Ren, but I'm drawing back a few years to my uni days, The hash itself is stored on CPU memory, so it can do a very quick lookup of the keys. But once it finds the key, what it's finding, what it's attached to is a memory lookup address. And then it has to go into your RAM or your hard drive or wherever it's stored and actually do a hardware lookup. It's got to reach out across the motherboard. It's got to reach out across the machine layer, across the hardware, and then pull that data from somewhere. And this is what you're talking about, the efficiencies. Obviously, it depends where the memory is. It depends on what the system configuration is. But the idea is that across the board, generally, your CPU memory is going to be the fastest thing that you can access because where the calculation is happening, it's right there. So if you can put your value in with the key for your map, then there is no lookup. You've just got it. When you find the entry in the map, you've got the value.
Yeah, exactly.
I'm confused about the relevance score thing, because surely that's a score that's calculated per search, isn't it? Like, is that just a hard-coded number?
I think that's where we would do search
search,
like search normalization, right? Like if you've got 100 people searching for using different terms, but they actually can be normalized to the same thing. Like you look up software developer, I look up software engineer, you look up junior engineer, they look up junior developer. They can all be normalized to the same search.
Right, but well, that's one search. What if I start searching for bakery? Like I think that's what's confusing me is because like how is a relevance score just like one number for like all searches, or is that a number that's being?
So this is more maybe coming to a little bit about how kind of search is modeled. So eventually we want to come out with like a model. Basically, after you're doing a retrieval, basically this keyword, you find all those jobs that are related to this keyword or this query, and you eventually want to rank them. And after you rank them, what you wanted to do is that eventually each job will have a particular score against to that particular query. And you want that to be just a number. And then all you need to do is just sort them by that. So the relevance score would be how relevant is this job against that particular query, let's say accountant. So.
And you said that like each job would have a relevance score for each query. So is that what kind of training the model is? Like finding a relevance score for all of these different queries?
Yes. So we would use the model, the machine learning model, combined with some other kind of basic filters and stuff to come up with a relevance score at real time for that particular query. So I can sort of maybe going a little bit around, let's say we receive a query called accountant in big corporates, something like that. So what we need to do at that time is first doing one pass to against all this 200,000 jobs, and then find all the jobs are kind of somehow relevant to that. So let's say this gives us 2,000 jobs returned. And then we need to look at those 2,000 jobs like in real time and just look using a model to run some kind of algorithms, and then the output will be a score, say, this job will be 0.9, it's very relevant. This job is 0.2, that's less relevant. So we basically got like 2,000 scores, and then we just rank them by that score.
Right. So the training of the model is improving its accuracy on being able to get that relevant score correct.
Exactly.
And also finding the jobs which are even a part of that, like just in general, right?
Which I think is where the filtering and stuff comes in, right? Like you're narrowing down your search to a smaller set of data so that the model has less things to interrogate. So the accuracy is what the training is. And then all the filtering and all the engineering parts that Ren was talking about before, like the radius search, that kind of stuff, is about efficiency. It's about reducing the amount of things that the model has to iterate over to be able to produce your results.
It just blows my mind because like we're talking about searching, ranking, and hundreds of thousands of jobs in a matter of seconds.
Nanoseconds.
Whereas on the front end, you'll have a list of 30, 50 items and it'll be slow. Like it just blows my mind how much with the work we can do in just like a snap of a finger.
Yeah, I'm still kind of stuck on that too. I'm just trying to picture. It's been a while since I've touched Java, right? And there's oodles of technologies out there. So, but I'm just sitting here going, what does that code even look like? To be like, no, don't write the data here. I want you to write it to the CPU cache. I'm like, so that's something that's like supported by the language. It was like, I didn't know that was the thing. And then you got to, I can't even.
I think that's where, like Ren was saying before, having an understanding of what the language is doing and how it works allows you to come up with these kind of creative solutions, right? Like having a fundamental understanding that your hash map is something that is looked up on the cache. So inherently, if your value is part of the key, then it's going to be in the cache.
Yeah, I think that's totally right. So I when I joined this team, I had this kind of feeling that I was being a bit kind of lazy before. So before, like I was just
that's how I feel right now.
Yeah, absolutely.
Kind of, there must be a library that does this. I might just spend a lot of time looking. This library does it. I just use it, and I don't have to think about it. And then a recent, like another engineer joined our team, kind of had the same kind of comment, saying now you're forced to really think about, like where you lay out your data, because if you're not careful, you can still implement the same algorithm, do that, but it will be like a magnitude slower. Our kind of 95p latency for search requests is 15 milliseconds. That is very, very fast. Think about in that 15 milliseconds, you need to go and do initial filtering of order to find that, retrieve those jobs that the first run cut, that jobs are relevant. And then you need to go to each individual candidate and do a scoring and then combine them together and also render JSON payload. That's a lot of work.
That's crazy. 15 milliseconds.
What's the metric for fast, slow, and like normal? What are the rough numbers?
So I would say like 50 milliseconds to run a search. It's pretty fast. We got some search requests that returns in 8 milliseconds, and there's some slow ones like maybe takes 200 milliseconds. That's kind of
slow. He says slow.
Mate, if I could get just my standard like database read queries to 200 milliseconds, I'd be stoked. It's really funny hearing about these kind of optimizations. Like right now, there's a particular domain that I'm working in where we're thinking about changing our underlying database technology because the sorts of queries that we want to run, it's a non-relational database, and the sorts of querying we want to do is across really in a relational format. And it's like, well, we can't really do that unless we iterate over everything. Whereas if we were using, say, SQL, you could just index it much nicer. You could have keys and joins, and it would just be quicker to look up. And it's funny that it's like my optimization at that level is just magnitudes. It's still magnitudes slower than the kind of optimizations we're talking about for AI. It's nuts.
Yeah, I was going to ask Ren, would you consider yourself to be a big data engineer? Because it sounds like the challenges that you're dealing with are the challenges of big data.
Yeah, I would not call myself big data engineer. I think, well, that's just my kind of definition. So what I see as, so there is a lot of people these days doing like being a data engineer. Like a data engineer in the AIPS point of view is that more around they are processing a lot of data coming from being produced. So for example, we track every single searches that the candidate did. We track all the clicks and impressions. So that's a lot of it. So impression means, when someone scroll through the job search page, they look at one, like if that job stay in the screen for 3 seconds, or they will track that as an impression, for example. And then, so that's a lot of data coming. So the data engineers more like, I feel like they would ingest them into a data platform and make them usable for other services, that kind of things.
So theirs is more about how to ingest large volumes of data, how to store and structure large volumes of data to make it accessible, and all of the platform engineering around that. Whereas yours is more about how to interrogate that data efficiently, how to restructure it for specific use cases, and solve those kind of computer science problems that happen to consume that data. Exactly.
So for our use case is how do we make those available during search time, and then how do we quickly scan those through those jobs data quickly, as efficiently as possible. So I would kind of call like myself, like more a system engineer. So basically thinking about we are building a search engine or database, and then the other teams around us they would consume our service. So they would sort of use, if we are the Postgres, so we build the Postgres, and then some other team would use that database so to build products. Something like that.
Cool.
How is that? So if you're making the engine, I assume that's just like its own service, right? How are other teams then communicating with that? Is that just via just like a regular APIs and stuff like that? Like, how do you even send a query to this AI model?
Yeah, so at the moment, it's actually quite simple. So we keep it really simple. So it's just for our search, it's just a JSON kind of REST API. So they call us with a search query, /search, and with a bunch of parameters, we'll say, search query, like keyword is what, location is what, salary range is what, and blah, blah, blah. So that's an API contract we provide. And then that's what we receive. And what we return is basically a JSON response with, the jobs that matches this query, and some analytics data and things like that. So
okay,
I found the sort of working kind of this one layer down really fascinating and really refreshing. And I know it's probably not for everyone. I've talked to some of the engineers I've worked in the past in other teams, and they're like, oh, no, I don't want to touch it. I just want to be able to, consume that nice JSON API. I call you and you can give me a nice JSON. I can render this HTML page, and I'm quite happy about that. It's not for everyone, but maybe for myself, I think it's really a rewarding journey. So be able to understand how the computer actually works, and be able to using those implement some of those algorithms and make it run more efficiently. That's really rewarding. But at the same time, also it's a kind of a great learning to kind of venture a little bit out of your comfort zone. So and I think another point I want to mention is these days, because the kind of engineering world, it seems it's evolving very fast, and we've got those big players like AWS and other cloud providers or database. They provide those kind of easy to use service and make us a little bit lazy. Like we think, okay, you can just use that service and you can build something quickly. But when your system need to scale, you've got those complexity around it. So I think it's really important, like for engineers these days, to really kind of step back something a little bit, look at how the fundamental works, and so they can be more powerful and creative to build sort of more scalable systems.
What sort of background do you think someone needs to get into the role that you're in? Do you think it's like what requirements would you say you have to have, or is it something that an experienced engineer could learn in the role?
Yeah, I think mostly it's just you need to have a strong interest in kind of system engineering or computer science. I think that's the only thing. So I did my computer science degree like many years ago, but I've never had to use a lot of things I learned into this job. So I only sort of joined 3 years ago, and I knew nothing about those kind of things that we talked about before I joined. I learned on the job, and it took me a while to get up to speed, but I don't think there's any big barrier as long as you're really interested in kind of understanding, how to lay things out in memory, and why you're interested in why this hash map implementation is faster than the other one, that kind of things.
You have to be passionate about understanding the inner workings of things, where a lot of engineers are like, no, I don't want to know. I just want to build the cool thing. I want to build I want to build the UI. I want to build the API. I don't necessarily want to know, the inner workings of a hash map.
Most engineers, I can't say every engineer, but I would say most engineers would be really keen to understand how things works under the hood. I think I'm definitely one of them. And I'm just kind of recall like comparing my sort of experience in the past where maybe I was working on some kind of search functionality, and I was using something like Elasticsearch to build something. But the frustration I had was I kind of need to read lots of documentation on how the syntax works. But I don't have a direct access of how that behaves. So I kind of need to guess it. And I found like most engineers would be very uncomfortable in that zone. Like you kind of know a bit, your documentation show you a bit, but you don't really know exactly how that works. But right now, sort of working in the search team and sort of working on our own search engine, I feel very kind of empowering and really kind of rewarding, because if I wanted to know how that works, I can dig into the code directly. It's plain Java code there. I can even put a breakpoint in there and run the code, and I can know exactly what it does. For many, many years, I feel like I haven't had an experience before. Like these days, is a lot of time you use the database, you use the caching layer. It's all of the systems, but it's really hard to put them together. You just want to run it, understand how everything fits together. It seems to be getting harder and harder these days.
Yeah, it's really fascinating.
Where could someone go to figure out if they're interested in this? Because you said like you need to have an interest in the inner working of things, but if someone doesn't know those things or knows much about it, it might be hard for them to even know if they're interested. So where could someone go to figure that out, learn some of that stuff?
Is there like a codewars.com for computer science problems or something like?
Yeah. Oh, like for me, for example, I have no data science or any sort of, background or knowledge in any of that. I didn't go to uni. So where would I go if I wanted to figure out if I was interested or just learn some basics that could get me an entry-level job into AIPS or something like that?
Our director of search and technology, Mark Pritchett, so he wrote most of the initial version of the search engine. There was a talk he did in a Melbourne JVM kind of meetup. So it's on YouTube. I'll share that kind of in the show notes. He talked a lot about some of the fundamentals and stuff, and there's a lot of links he also shared about some of those. I'll share that. But others is just that if you are interested, you can go to some kind of like the GitHub repository. So for example, there's Postgres, there's some Redis. So those database and systems, they are sort of open sourced in a way. You can go in to look at those code, and initially it might feel very intimidating. Oh my God, I'm looking at the code of Postgres, but take your time. It might not be that intimidating if you go and look at it. Things will start making sense, and so you can even contribute to some of the issues or merge requests and things like that.
I would also recommend looking up, I can't remember the exact names, but I'm pretty sure they're Code Wars and Code Carter. They're two websites that are based around the idea of introducing you to very small technical problems, like what sort algorithm, what's the most, essentially they give you a data set, you have to sort that data set within a certain time limit, and you write your sorting algorithm, and then they run it, and it'll tell you how efficient it was and whether or not you pass or fail. And then you can look at other people's implementations. So you can show me the solutions, and you can look at everyone else's way of approaching that problem. And they've got problems that scale from quite straightforward to sorting to very, very complex. I would recommend jumping in there, because if you don't enjoy solving those problems, probably might not enjoy the level of challenge that Ren's team faces, because the scale would be a lot larger, I think.
And because you mentioned two different databases, so looking at how the code is written in databases and stuff is, I get that, but is there, none of those have anything to do with AI? So is knowing about AI and basic understanding of that required, or is that something you can kind of learn on the job as long as you have some interest in the inner workings of, databases and all that?
Yeah, so if you're kind of, for my team, I feel like when I joined the team, I actually know very, very little about AI. I think for AI, machine learning kind of knowledge, unless you are kind of, your job would be a sort of data scientist or machine learning engineer, you don't really need too much of that knowledge. But if you either just wanted to work in our team, or if you want to just interested in kind of learning some machine learning, there's a lots of kind of video tutorial on YouTube, and there's lots of open source resource like Hugging Face. Hugging Face is an open source model kind of repository. So they provide a lot of open source models, and then you can go to they've got tutorials on how to use that. So as long as you know some basic programming, like either Python or JavaScript or whatever, they've got some tutorials on how to use a model, and they'll tell you how the model works. And I think that's a good kind of starting point, and trying to maybe use some existing models, calling the API and see how that works. And yeah.
Cool. That's interesting. It certainly makes getting into these sort of roles more tangible. To me, it just sounds like I don't need to know all of these crazy things like we were just talking about off the bat, like
neural networks.
Yeah, right. And because I
notation.
That's right. Yeah. I mean, it sounds like it's a lot more tangible as long as you have some sort of basic understanding and interest. Yeah, like you said, there are things that you can kind of learn on the job. That's good to know. Really, really insightful.
Yeah, I would say there's definitely, I've gone through like those aha moments where, when I first joined the team, I don't really understand people talking about the transformer models. I don't know anything about that. But kind of once you start reading some of those materials, over time, you've got your moments. Okay, now I get it. Like, why it's like, yeah.
Sounding pretty good.
Yep, there was a lot to learn there. That was a great episode. Thank you, Ren, for joining us. That was
thank you so much.
Really insightful.
Yeah, that was fantastic.